All right, you guys ready? Okay. So we forgot to get snacks yesterday during our afternoon break. Totally forgot. Don't let us forget to do that because they put out snacks at 3 for the afternoon. So Manuel, I just forgot.
And don't forget to tell us that
Right.
who's coming, because
We're just not.
drivers. So.
Yeah. So just because that's our problem, it doesn't have to be your problem. So yeah, remind us. All right, so we're going to measure absorption this afternoon. So let's think about why that is. So I actually decided to throw out the Icam. Has anybody heard of the Icam? Innovating Cavity Absorption Meter? Yeah. It was here in the last class. And, oh, don't go, ooh. Yeah, we just published a paper showing that it doesn't work, which is so sad. It's just the saddest thing. So I have it on here as a reminder. If anyone wants to talk about it later, we can do that. But I'll be talking about the AC meters and using a laboratory spectrophotometer because that's what we're doing in lab today. So before we do that, I want to just kind of go back to thinking about how one would measure absorption in perfection land if we could be there. And then we'll go to reality land, which is where we are, and just understand the difference between the two. Okay, so let's think about a slab of material, a thin slab of material. We'll talk about how thin needs to be. And we're thinking about making it thin enough so that if you're sending energy in and you're thinking about a packet of energy, and I'm going to use the word photon, and Kurt's going to tell you why you can't use photon anymore, but for our intents and purposes, we'll just talk about it right now, but it has a probability of having one event happen to it in that slab. It will either be absorbed, or it will be scattered, or it will be transmitted. But it will not be scattered and then absorbed, and it will not be scattered and then transmitted. That's how thin we have to make our slab so that only one thing can happen to this at a time. Okay. And that there's no shading, right? Like, so you can't have multiple absorbing opportunities. So it's got to be, we have to make sure that what we measure on that's coming out has only experienced one event or the absence of one event. All right, so we'll have some incident power coming in to this, your light bulb, your LED. And then we will have the amount that's transmitted coming out of our slab. And if the power coming in and the power coming out are the same, that means nothing happened. There's no attenuation, there's no loss of energy, right? That's pretty obvious. But if the transmitted is less, then there is some sort of attenuation. That means there's some absorption or scattering occurring. And if only the loss is only due to absorption, then we just say, oh, the loss was absorbed power, right? So we'll make this assumption that there's no scattering. And so if that's the case, when we measure incident and transmitted, the difference is going to be absorption. But we just have to make sure there's no scattering, either by not having anything scattering in the medium or by figuring out what the scattering is. Okay. So if there was a non-absorbing medium and there was loss due to scattering, the redirection of energy, and we did not detect that in the transmitted, then the difference between incident and transmitted is the scattered power. So that means that even though this got scattered in the forward direction, we can't include that in the transmitted measurement. Right? Because otherwise we're going to underestimate scattering if we collect scattering. So when you're building sensors, you have to be very careful about this collection here and what it includes. All right, the reality is there's probably both going on. And so the difference between those is the absorbed and scattered power, and we call that the attenuated power. So you can, just by conservation, we could say what came in and this is what goes out. It's either transmitted or absorbed or scattered, right? Conservation energy. And of course, we've ignored re-emission and fluorescence and things like that at this point. But that's going to come into play for some instruments. All right, so let's just do a little derivation of absorption. And it will be the same for scattering. And I think we'll probably go through it when I talk about scattering later in the week. But once you see it once, it's pretty straightforward. Okay, so we have some definitions. And it's going to be, these definitions will also be in your lab handout. If you miss them, this is also somewhere. So there's something called absorptions, which is that fraction of the incident power that got absorbed. And we just define it by the ratio. It's the fraction of what got lost over what was incident. Absorptance with a T. And if there's no scattering, we can say, well, I can't measure what got absorbed, right? So, but I can figure it out by just looking at the difference between what came in and what went out. And the absorption coefficient, small a, is the absorptance per unit distance. So the thickness of our slab is the distance over what is occurring. And so it's going to have units of per meter, right? Because absorptance is dimensionless. All right, and so if we rearrange this, we can move this over, and we can express the absorptance by the fractional change, right? Which is the incident minus the transmitted. It's, we're going to see a loss, so there's a negative sign, over the power. So when we start to see delta signs, we think about derivatives. Okay. And so I'm going to just move it. I'm just going to swap this for now because I think that this is just, I don't know, for me, it made a big difference when I thought about things this way when I was sitting where you are. This is a fractional loss over this layer. It's proportional to what? The fractional loss in power over distance is proportional to what the absorption coefficient is, but it's proportional to the power, the radiant energy, right? So what it says is that the more radiant power you have, the more you lose. Because the absorption coefficient is constant. If you have less radiant power, you lose less. Because if that wasn't there, I can't block it out, it's on my hand, but if that wasn't there, if it was just the fractional loss as a constant, then it doesn't matter how bright your source is, you're just going to lose, 10 watts. But you don't. If you have 100 watts, you might lose 10. If you have 10 watts, you might lose 1, right? So you have to, so it's this proportion, because this is constant, it depends on how much is there. And so when you look at, say, how light disappears in the ocean, you drew it in there. I just took pictures of the diagrams you had on the board, which we'll look at the end of the class. And you drew the exponential decay, it loses more light in the beginning than at the end. There's more light at the top of the water column than at the bottom, right? So it's the same concept. The more light there is, the more you lose. Okay, so I just want to make sure that you get that. And that was figured out very early. Okay, so if we look at the equation this way, it says that the absorption per meter times the thickness, so is related to this the gradient over what's over the magnitude of the radiant power. And so because we see the deltas, we should immediately think about taking that as the limit goes to 0. And so if we take this as the limit goes to 0, delta x goes to 0, that puts us into intervals. And so what it says is that if you integrate the absorption coefficient, which we're going to assume for now is constant, over that very small slab, which we should be able to keep the absorption constant in that slab, then we can just integrate the radiant power over that thickness. All right. And so the integral of AdX is just A times X. We're going to evaluate it from the beginning to the end of the slab. The integral of 1 over x dx, or 1 over phi phi, is the natural log. Okay, you can just look that up in your math book. And then you can integrate it. And so then once you start having natural logs, you have all these really fun rules with natural logs, and that's what we're going to get to next. But so if we evaluate this, we're going to get A times x minus 0, right? Minus the natural log of x minus the natural log of 0. And how many people remember all the differences of natural logs, the ratio of natural logs? Yeah, just write it down, make a little crib sheet for yourself. This is where it is, we're just repeating this up here. So it turns out that the power at x is the transmitted power, right? Because that was on this side. It was incident at 0, transmitted at x, right? And the difference in natural logs is the same as the natural log of the ratio. That's the rule you got to remember. And then we can bring our x over here. And so we can find that our absorption coefficient is inversely related to distance and the natural log of the transmitted over the incident radiant power. And that defines how you are going to design an absorption meter. We need to know x. We need to know how much power is incident on our sample and how much is transmitted through our sample. So now you're ready to go out and start a company. And so what I want you to do is keep this little equation close at hand. You could write it on your hand, or you could bring it with you to the lab. And then when you look at these instruments, I want you to think about how the instruments were designed so that you know what this is, so that you can always know how much light is incident on your sample. And if it varies, how do you keep track? Oh yeah, you shine a light, it varies. Right, I know, this is so painful. I feel your pain. So I gotta have something else that's telling me that my lamp isn't varying. So when you're doing your lab, think about it. Where is it measuring the intensity of the lamp? Okay, and then I have to measure this. What kind of detector? I need a detector that is only going to miss the absorbed radiant power, not the scattered, not scattered. If there's any scattering that happens, it needs to be detected. Otherwise, the loss appears to be absorption when it's really lost due to scattering. So again, look at the instruments. Like, are they doing a good job? Do we have a ruler? Can we get a handle on this and on this? Right? It's only 3 terms. How hard can this be? All right. So let's look at some absorption through some particles, because we're just going to follow this. And so I'm going to move some stuff around. And then I can say, well, the ratio of the transmitted to the incident is really just the exponential, right? I love natural laws and exponential. They just move back and forth so beautifully, right? So what that says is that the transmitted radiant power through a particle is going to decay exponentially, right? All right, so, and I can say that the power anywhere in the distance is what's incident on the outside times this exponential, which is very powerful. And people also wrote this on the board, thinking about light decaying with depth exponentially. But I'm telling you that you can think of it the same way in a particle, an absorbing particle. All right, so, all right, I'm not very good with making nice diagrams in PowerPoint, but that's the best that I can do for a wave. It does have a constant wavelength. I actually put it up to a picture of a ruler to make sure it has an amplitude. Okay, it's big relative to the particle. These are not to scale, but you get my point. So this wave intersects the particle. It's going to enter the particle. And what's going to happen to the amplitude of that energy? If absorption is going to occur, the amplitude will go down because you're absorbing energy and amplitude is proportional to energy in a wave, right? How is the amplitude going to go down? Is it going to go down linearly? No. What's it going to do? It's going to go down exponentially. How am I going to draw that? Took me a while. It goes down exponentially, right? It exponentially decays. So we've done nothing with scattering, so there's no change in wavelength. Wavelength, things shorten up and lengthen, but that has to do with scattering. This is just to do with the amplitude. So in fact, the distance between the peaks is constant, it just doesn't look like it. And if it isn't, it should be. But the amplitude decays exponentially. So what comes out on the other side is the same wave, the same frequency, the same wavelength. It's just damped because it lost energy in this particle that absorbed it. And it comes out the other side. So this could be happening in a particle, and it could also be happening in your cuvette. If you had a constant absorption in here and no particles. Okay, yeah.
Over the incident, that's the fraction of how much is through absorption, but then how do you
I have told you that this particular medium is non-scattered. Because as soon as we start having actual, real, non-theoretical media in there, we're going to have to think about how to ignore it, how to either measure it or account for it or exclude it or correct for it. So hold that.
Okay. Sorry, I just
No, don't be sorry. There's no, I mean, this is exactly it. So this is where things get complicated is I was like, oh yeah, and there's no scattering, and I just went right on, right?
Okay.
Right? And so there is. Right. Okay. All right. So now we've got 2 different media, which I've cleverly colored differently. Which one do you think has the highest absorption? The darker one. All right. So we have the same wave, it's incident on this, and look at the exponential. Okay. So this one has a steeper slope, a steeper exponential decline, And so by the time you get down here, there's almost no light. Is that the same thing? Okay. All right. So you can imagine that you can have enough, either a high enough absorption to make it so that nothing makes it out the other side, or just a little tiny bit of light makes it out.
So little a is bigger on the darker green.
Yes, little a is bigger, and that's what is defining this slope, this amount of loss of light. So for these two exactly same size particles, the difference between them is the absorption coefficient. In this case, they have the same absorption coefficient, but they are different sizes. So what changed?
Distance and purity.
The path length. So path length, as the path length increases, what's going to happen to the amount of light at the other side? Well, more absorption, right? They have the same initial slope, but this one continues out longer, and so you can lose all of the light or almost all of the light just because the path length is longer. So if you're designing an instrument, you don't want to have a path length as big as this room because you'll have nothing to detect on that side.
Success.
Huh? Right?
Well, we successfully detected nothing on the other side.
And what is success? Exactly what we were planning. So that the transmitted light is proportional to the absorption coefficient, and it's also proportional to the path length through it, which is what we actually just proved, what we derived. Right? So yay, everything makes sense. Okay, so this is where we can start thinking about absorption and an absorption spectrum. So here's an absorption spectrum. Phytoplankton, we've got our blue and red peaks, we've got these other little peaks from other pigments that play in there. This is actually a harmonic of chlorophyll red peak. There's another harmonic of chlorophyll red peak. That's probably carotenoid. That's the blue chlorophyll. It's in the cell, it's packaged, it's in a phytoplankton membrane. And here's the cell. It looks green because it absorbs less green. It absorbs blue and red. It doesn't absorb green. So to our eye, it looks green. So if you send blue light through versus sending sort of yellow light through, so blue light will be here, yellow light will be here, what do you predict it's going to look like if we look at those waves going through? What? Absolutely. July20 says, right? July20? Okay. Says that it will be absorbed much stronger in the top diagram and less in the bottom diagram, which means it's going to be a stronger exponential in the top and a weaker exponential in the bottom. There and there. Excellent. Okay, so there's something called pigment packaging, and I want to go back to this picture here, where we might be looking at the same wavelength, but we just have a higher absorption coefficient, and to the point where we don't get any light out, right? And let's say that this is 440 nanometers. And then let's say we look at 441 nanometers or 439 nanometers. You might also find that to be the case, that the absorption, even at those wavelengths, is also similarly high so that you don't get any light out. Because either your absorption is so large or your cell is so large that you might get nothing out the other end. Whereas if you had a smaller cell or a lower absorption coefficient, you could detect the difference between 440 and 441. Because 441 would actually have a little more light getting out, a little bit lower absorbed power. that's the idea behind pigment packaging. And so, how many of you have read these papers by Morel and Rocco about optical efficiency factors? Read them. They're great. They're just thick, like intellectually thick. But so what they did is they took, they modeled a variety of cells from, a solution all the way up to 64 micron diameter particles, spherical, perfectly uniform absorption. They modeled their absorption coefficients and then normalized it to 440. And what you see is that when you have a really small particle, a very small path length, you always have some amount of transmitted radiance on the other side, such that you can distinguish the difference between absorption at 400 nanometers, absorption at 401 nanometers. There's enough difference because the absorption is relatively low and the transmitted is high, and so you can detect small changes in transmission. And in that cell, you can distinguish very sharp peaks of your absorption by various compounds or pigments. But as you take that same cell, which has the same absorption coefficient, but is a bigger cell, the amount of energy that gets transmitted through is so small that it flattens the peaks that when you measure the transmitted, it's difficult to distinguish because basically it's all been absorbed. Or it's even shaded so that some, I'll get to that in a second. So you find these peaks get flattened. Even at the low absorbing wavelengths, it starts to sort of fill up and flatten out. And so this is a theoretical study, but what's really interesting is that you see this in cells, natural cells. Packaged cells, which have lots of pigment and are big, compared to small cells that have a short path length and don't have a lot of pigment in them. And so the shape, how peaked your absorption curve is or how flat it is, tells you an awful lot about who's doing the absorbing. Are they big cells? They have a lot of pigment in them. And it turns out that if you look at this absorption and you normalize it to the concentration of pigment, so a pigment-specific absorption, or you can do it, pigment-specific absorption, and that's where the star comes in. That says that we're measuring the absorption as a function of pigment, which is doing the absorption. When cells are very small, their absorption per the number of chlorophyll molecules that they have in them is really efficient. Every chlorophyll molecule is doing its job. The light comes in, it gets absorbed. Some of the light gets transmitted, but every chlorophyll molecule is absorbing. As you get to bigger and bigger cells, you've got chlorophyll at this end, chlorophyll at this end, light's coming this way, a lot of absorption, a lot of absorption, a lot of absorption, a lot of absorption. By the time you get to this end of the cell, there's a chlorophyll molecule like waiting for some light to come its way. And maybe none comes. So it didn't get to do its job. So it gets, in the calculation of absorption per chlorophyll, it shows up because it's a chlorophyll molecule, but it didn't do any absorbing. And so the efficiency of absorption per molecule of chlorophyll goes down. So then you say to yourself, well, why would a cell invest so much energy in making all this chlorophyll if that chlorophyll isn't going to do anything? So I ask you, why would a cell do that?
Protect from photo damage?
So it could protect from photo damage. It could develop pigments that actually provide a sunscreen to protect the nucleus, the DNA, the mitochondria, from photo damage. And by doing that, at a certain wavelength, particularly UV, it could protect the cell. It's another reason it might just pack pigment in itself.
to divide?
Yep, it's actually, that's true. So it's replicating and it's getting ready to divide. So that becomes very interesting because that means its absorption efficiency changes depending upon what phase of the life cycle it's in. So you could look at this absorption for chlorophyll ratio, how that changes through the division, replication and division, and you could actually use that to tell you something about growth rates in the occurrence of division, because you're going from big pack cells to small pack cells, right? So again, another opportunity. What else? Why do they even absorb light?
To produce additional energy.
Yeah, photosynthesize, right? So they want to photosynthesize. And what if there's not much energy? What if they're down deep in the ocean and there really just isn't much getting down there? You want to make sure that everything that hits your cell gets absorbed. You pack on. So that's called photoacclimation. The response of cells to low light. They make more pigment. And each pigment molecule isn't that efficient, but they're actually less concerned with that than they are with, I want that, all the energy that comes in. So these are all natural responses of phytoplankton taking advantage of exactly this process. And so you can measure the absorption spectrum and look at the sort of flattening of the peaks to tell you something about who, how big, what phase, growth radiance, all sorts of really interesting physiological and ecological information just in the flattening of the absorption peaks.
Can I ask a question real quick?
Yeah.
So if your absorption is what?
If you what?
Like if the absorption equals what?
Oh, it means
That means
absorb
all
everything.
light within.
Yes. Yes, it means that.
And if you
Yes.
put a super bright light in there, nothing would stick it through.
Depending upon the, yes, right, depending upon, the flux of the, I mean, for that scenario, yes. The optical efficiency is one. Everything that goes through gets absorbed. It's basically, you have a three-dimensional cell, but in a two-dimensional space, nothing gets through. Yeah. Efficiency of 100%. So we're going to do some modeling, similar modeling to this when Emmanuel runs a V modeling lab, where you'll actually get to model what's happening on a cellular basis. Yeah.
Could you go through the list with what you can get from the flattening in the peak again?
Size, internal pigment concentration or absorption. You could get growth irradiance if it's a higher low light cell, because it would put on more pigment if it was in low light versus high light. If you look at cells that grow, replicate, and divide, there will be changing pigment per cell, changing pigment per cross-sectional area, changing pigment per volume. The size will change. So all of those little pieces, each will impact the absorption spectrum. So the question is, which one of those things, which two of those things, or which three of those things might you be observing? So you will be some ancillary information so that you could say, oh, this signal, the peaks got flatter because these cells were brought up from deep in the water column, and they were experiencing very low light, and suddenly now they're high light. Or I looked at this cycle over the day-night cycle, and I saw that it was responding to radiation, or these cells are dividing, and I can resolve that. Okay, so this pigment packaging, again, so they've normalized the absorption spectra at 440 to compare the shape. And this one is for the small cell, and this one is for the big cell. And you can see you've got a nice sharp peak for the small cell and very low absorption here. The packaged cell even appears to have very high absorption. It's just, there's some low pigment in there, but it's so big that it becomes artificially higher absorption because of that. And so if you look at this blue to red peak ratio, if it was just chlorophyll, and it was just chlorophyll by itself, there's actually just a constant ratio of absorption between those two absorption peaks that are driven by the electronic states. But when you start to put them in the cell, and you start to package the cell, and cell is small or big, that ratio between them changes, right? And so if you look at that ratio, you find out that ecologically, when you are in a region of the ocean with low chlorophyll, which would be where? What parts of the ocean have just a really low chlorophyll concentration, very low phytoplankton?
Subtropical gyres.
Subtropical gyres, right? In those parts of the world where chlorophyll is low because of low nutrients and eutrophication and all the reasons why we have that, you tend to have a very large blue to red peak ratio, which means that the cells are not packaged. Turns out they also tend to be small. They're small because there's no nutrients. And small cells have an ecological advantage, physiological advantage to low nutrient waters. Those also happen to be pretty stratified waters, very high height. They have no need for excess pigment. Small cells, low pigment, they tend to have very unpackaged absorption, very strong peaks, and very efficient absorption for chlorophyll. At the other end of the oceanic regime, where your chlorophyll is 10, like out here, we see a very low ratio of blue to red. They're almost equal in these types of waters. So this is ecological concentration. This is water column concentration, just so you're very clear on that. So this is like an estuary, this is the open ocean, this is the probably subpolar gyres. On this end, we're looking at cells that look more like this. They're flatter, they have a low blue to red peak ratio. So what do you, if you say that, what do you know about those cells immediately from this absorption? What size are they? They're big. What's their pigment concentration?
High.
Probably high, right? And so, so you tend to find those types of cells in very nutrient-rich environments. They have excess nutrients. They can make extra pigment. They're in turbulent environments, right? The subpolar gyres are turbulent. Coastal waters are turbulent. They get mixed down in steep. They're like, whoa, I need to make some pigment. They get mixed back up. Like, yay, way too much. Like, right? But they're very dynamic. They're big cells. They're diatoms. They're the big diatoms. Right? So you can sort of use these types of relationships to tell you something about, like, who do I have, right? What can I expect based upon what oceanic regime am I in? So the absorption becomes very powerful. Yes.
Is there any criteria to decide which way to normalize the spectrum, or?
So they picked the 44676 because that's the peak of chlorophyll. And the reason to do that is that all phytoplankton have chlorophyll A. And only phytoplankton have chlorophyll A. So it's very unique. Once you start getting into the beach area, like, I have fucus I have periodism, I have, like, so they all have different things. And so you pick the two peaks based upon what you know everybody has. Okay, oligotrophic, eutrophic, good. Small cells, large cells, okay, everything else is good.
So can you just explain that for larger cells, like I said, that for the small cell is more likely to have A and B, and the large cell has C, D, and F, or will they also have A, B, and?
So that's very interesting because if you go to the picoplankton, they tend to be cyanobacteria and tiny chlorophytes. So cyanobacteria have phycobilly pigments like phycouracil and phycoerythrin. They live at different places in the water column to take advantage of the light at those areas. So they, the bacteria, phytoplankton, they have a different suites of pigments. They also tend to live deeper in the water. The small green chlorophyte phytoplankton that also we find in these nutrient depleted zones, they tend to live higher. They have chlorophyll A and B. They don't have a lot of pigments in here. And what you're seeing in here is real. They don't have a lot of pigments here because they tend to be tons of light. There's plenty of light here. We're in the open ocean. What don't we have in the open ocean in terms of an absorber? CDON. So there's not a lot of competition for the blue light. So they can make it by with mostly blue absorbing pigments, right? But as soon as you get to the coastal waters, that blue light is gone. And for some of these phytoplankton, they have this absorption, but there's not a lot of light there for them to be absorbing. So they're taking advantage of all these pigments in here that are absorbing green light. And they do have very different pigments. Taxonomically also.
So, like, would you say it's generally similar based on where they're located in the water column, like deeper phytoplankton typically have the same pigments?
If they don't have the same pigment, they have something that's in that spectral band. So if you look at the sort of pigment-based taxonomy, it's pigments, people use them a lot. They're like fucoxanthin, diatoms, paradenin, gunflagellates. Well, paradenin is gunflagellates. The fucoxanthin is diatoms and a lot of other things, right? But so, you know, and they don't totally overlap those two, but they're close enough that the pigments that they have are allowing them to take advantage of that region of the spectrum. Yeah. Okay. So yeah, you can do the same thing, not with size, but with like the intercellular concentration. That's what I mean about photoacclimation. You can put on a lot more. If you have a lot more pigment per cell because you're growing in low light, you're going to have a flatter peak. Right. So the shape of this can tell you size, or it can tell you the internal concentration. Use other information to figure out which one. Okay. So measuring absorption. We really want to be able to separate out, you know, who's there and use their absorption coefficient to tell us how many phytoplankton, how much non-algal particles, how much CDON. So the first thing that is so helpful is just to separate them. Just separate the water into particulate and dissolved. And this gets back to the question of what's the size of your filter? Well, yes, pick your filter. Be thoughtful about why you pick your filter and be honest about what you're missing, right? If you use a 0.7, that's great, but know that colloids and small particles are going to be in your dissolved. If you pick 0.2, you're still going to have chemically particles, but closer to dissolved, right? So just to be thoughtful. Don't just take something that use 0.45. You're like, okay, why? Oh, that's what we have in the cabinet. So think that. But so separating the particles from the dissolved really helps. It also allows you to concentrate your particles onto a filter. And when you're in a really dilute medium, sometimes you need to do that. Right? So what I'm showing you here is what we do in a spectrophotometer. If we're using an absorption meter, you want to think about your path length. You can have a short path length absorption meter in the water, or you can have a long path length. But when it's very dilute, you need to have the ability to actually measure something. And so, okay. So this is a cuvette. It's filled with a solution. It has a path length. The cuvette, we'll call it L for length. That's what we'll be doing in lab today. So spectrophotometers, just because I want to give you more jargon and more terms, and it's not my fault. I didn't design this. But spectrophotometers, instead of doing absorptance, which we've been talking about with T, they measure absorbance. That's what they output their data. They all measure the same thing, transmitted radiant power, but they output absorbance with a B, we're calling it, and hopefully we've been completely consistent in everything we're giving you. I think we have done it. If not, please let us know. This is the capital A italics, not bold. This is the capital A italics bold. I mean, there's only so many A's, and we can't use alpha because that's something else. So here we have it. And what are we going to use for area? Because we're going to end up having to use area. And I don't even remember what I did. I think it's not italic. All right. So remember we have absorbance is the absorbed radiant power over the incident. Well, the little a, the non-bold a, absorbed 10. That absorbance is log base 10.
Oh.
Thanks, spectrophotometer companies. And so we can relate them to the absorbance and the absorbance to each other. And you will hear absorbance when people talk about optical density, because that's the spectrophotometer they talk about. Your signal is an optical density. They're measuring really absorbance, but they provide you with absorbance. Not my fault. So you take your sample and you make a measurement of your absorbance. And then you also have to have some reference to subtract, or a baseline, because there's a cuvette. You certainly don't want to measure the cuvette, right? That we want to include that. And so, and you may even have a reference medium if you have, things that in here that you want to measure, like CDOM, and you don't want to include water in that. So you might use a reference water in the same cuvette, in the same orientation, with the same sides oriented exactly the same. Turn them. It'll be different. And so we have our absorbance of our sample minus our absorbance of our reference, and we find out that it's just the transmitted of the sample over the transmitted of the reference. Easy, easy. Okay. So in order to get to absorption, we had a nice relationship between absorption and absorbance. Now we have to go from absorption, or from absorbance to absorption. It's the natural log of 10, right? Because this is log base 10, of the absorbance divided by the path length. And if you take the natural log of 10, you get 2.303. So if you remember kind of seeing that equation, like absorption was 2.303 optical density over path length. The 2.303 is just the natural log of 10. You're just converting from the log base 10 to the natural log. Yes.
Just to clarify, in this case, the italicized A is the sample times.
It's this one, yes. Well, it could be, you could calculate the absorption of the sample and the absorption of the reference and then subtract them, but yes, thank you. Yes, you're formulating a question, your arms going out.
Yeah. So the A there is non-italics, non-bold.
It's the optical density absorbance
Okay.
from the spectrophotometer.
Right, so it's italics.
It's italicized without being bold.
Okay.
It will be the spectrophotometer plots and the file that it gives you.
Okay.
The file that I will be giving you to process tonight, for which you will calculate the absorption coefficient, because I'm giving you this. You have to make sure you know what this is. You will use this equation to calculate this. Excellent. Okay, but the cuvette is not an infinitesimally thin layer, right? And so what we want to do is, if we can't have it geometrically thin, let's make it optically thin. So we have 1 centimeter cuvettes, we have 10 centimeter cuvettes, we have 2, we have 5, we have all sorts of cuvette sizes. I even have 1 millimeter cuvettes, but I didn't bring them here because we're not going to have those thick samples, but you can buy them. So if you keep your absorbance on the spectrophotometer, you can see the value that's coming out. If you can keep it between 0.1 and 0.4, that's equivalent to a transmittance of about between 40 and 80%. 40 to 80% of the incident light is making it through, you're detecting it. That means you're pretty optically thin, you're not having multiple optical events in your path lane, and so we can say it's pretty good. It's really close to the true absorption. So we're just going to always want to keep our samples about here. If you get much higher than that, then you might have some self-shading within your cuvette. You've created flattened peaks in your cuvette, which means not reliable absorption measurements. Traveling along a long path, yep, okay. So just adjust the path length. So a clever thing to do is to take your sample and measure it in all your cuvettes and make sure that you're getting the same absorption coefficient in all of them. Because the material will always have the same absorption coefficient, right? You're just putting it in different vessels. But if you're measuring really, really high absorbance, then you could be in this sort of nonlinear where you're not able to measure all the absorption that's actually occurring. So it's not going to be doing that lab. You get a sample, figure that out. So typically, I use a couple of different path lengths when I'm measuring CDOM because it has really low absorption in the red, and really high absorption in the blue, and really high absorption in the UV. So I have to use a 1 centimeter cell to do the UV, 5 centimeter to do the middling, and then I use a 10 centimeter to do the sort of green to red. And then I put them together. So, okay. All right, particles. So now we're on this side. We're looking at the particles on the filter. And so we go from this really dilute medium with particles sort of suspended, then we put it on a glass fiber filter. And this is from, I'm blanking on her first name, Emmanuel Greet, and Greet Newcomen. Thank you. Greet did this really nice work on filters where she actually scanned them to see what they look like. This is what a glass fiber filter looks like. So when you buy a glass fiber filter and you're like, oh, it's 0.7 microns nominal pore size. You're like, that's not a hole, right? But basically, it's a tortured path, and on average, it collects 0.7 with 90-something% efficiency. But you can imagine as you load that on there, particles on there, you start filling in all those little gaps, and so it becomes nominally smaller the more you load it. So again, one of the rules of thumb is keep the optical density on your filter pad 0.1 to 0.4. Really good for the spectrophotometer. Also, it keeps you from overloading your pad and changing the size efficiency of your filter pad. Okay, so how many of you have worked on a spectrophotometer just measuring absorption on a spectrophotometer? 1, 2, 3, a couple people. Do you usually measure it in a mode where you have the light coming in, you have your detector, and you put a filter pad there? And you call that transmission mode, where it comes in and you measure what comes out? Or do you use an integrated sphere? You use a sphere. Sphere? No, not a sphere. Okay. So I'm going to show you the integrated sphere because that is, for particles, that is the best way to do it. And I'll show you why that is. So the sphere is coated with ferrous sulfate. It's highly scattering. It's like being in one of those scenarios that we talked about the other day with the particles and no scattering or no absorption where everything is white. It's like being in one of those. Okay, so we're looking down on the sphere. This is my filter pad with my particles of phytoplankton suspended or filtered onto it. So we're looking down on the top. The light is coming from the light source that hits a mirror and enters into the sphere and goes through the front of your sample. It hits your particles first before it hits the filter. And for those of you who've seen the white filter pads, they're white, they're highly scattering. What's going to happen to that light? So it's entering into your phytoplankton and other particles. What happens to it?
Absorbed.
Yep, some of it's going to be absorbed. the part that isn't absorbed, what's gonna happen to it? Goes into the glass fiber filter. What's the filter gonna do?
Scatter.
They scatter. They're highly scattering. They're white, right? They're scattering all wavelengths pretty equally. So they're going to come out. Some of it will pass through. Some of it will scatter out. Some of it will actually probably even scatter back. It's going to hit this wall and multiply scatter off the sphere. And if you looked in the sphere, which you cannot do because you will blow the PMT, but if you could, you would see just this highly lit sphere on the inside. And so it's basically just completely illuminated in there. And you're like, wait, that light's gonna go back through. So now I've measured my sample twice. And what about something that comes off here and goes here, and comes back? Now I've measured it 3 times. I've given it the opportunity to measure my sample multiple times. How do I know how many times? Because I don't want to know the measurement of incident and transmitted.
Timing of the photon.
That would be cool. Just send a photon at a time. Design that, there's cool instrument to design. Well, so, okay, so we call that amplification, like how do we correct for that? So it turns out we also have a reference beam that's coming in also. So this light's coming in, and you'll notice it totally misses the sample. It sneaks in behind it, comes in as a beam. And what's going to happen to that beam? Yeah, it's going to come over and multiply scatter off the sphere. And it's going to go through the sample once, twice, thrice, whatever tenses, you know. So it will go through the sample filter pad the same number of times as this part, as the transmitted beam, but it will do it 1 less because it didn't go through it initially. So the difference between the two is the absorption of the filter pad.
How do you measure, well, where is our optical sensor in this?
So the optical sensor, not well designed by my thinking.
Okay.
As I'm looking down the sphere, as I open it up and I look down, I see my filters here, I've got light coming here and light coming here. It's at the bottom. So if the filter falls, it falls on the detector, which is so bad. And if you put a cuvette in there and you spill right on the detector. And so we're going to be super, super careful. But yes, it sits under here. It's just a small photomultiplier tube. Super sensitive and very easily blown. So we have to make sure we never open the spectrophotometer. We never open the integrating sphere when it's running. It will, if you had that light anywhere near it, it would just blast it. So we're going to be so, so careful. But yeah, so it's basically detecting a portion of all of the light. So there's light fluxing in, light fluxing into the detector. There's an equilibrium between that. It's measuring that fraction. And so it's measuring, so all the light gets multiply scattered, and it measures sample reference, does the math for you, and just gives you the optical density of the photon in the samples.
Do the sample reference before you put it in the filter pad.
So first you do a blank filter pad as a reference, and it does calculates the difference. Then you put in a filter pad with your particles on it. It gives you just the transmitted radiance. And then you subtract the first measurement from the second, removes this effect, and you just get the green layer.
To clarify, it turns one beam of light on and then turns that off and turns the other on.
It's super fast.
Okay.
It doesn't turn them off and on. It does. It does. It's got like a little chopper. So there's the lamp over here. It goes ching, 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 while it's scanning wavelength. So it goes to 400 nanometers, sample reference, it actually does it dark as well. And it goes to 401 nanometers, sample reference dark. Sample, calls it the reference beam, and we also have the reference measurement, so it's kind of confusing. We'll call it the baseline measurement. The baseline measurement with a blank filter. So it does sample and reference beam on a blank filter, sample and reference beam on your sample. So you actually take two spectra and you subtract them. But it's very clever how this works. Also, because the sample you're having this really high intensity, you're able to detect very, very, very highly resolved measurements of absorbance. Okay. So the sample beam minus the reference beam is a single pass through the filter. And then by doing a blank filter pad, you remove the filter pad signature. But you can imagine that if you just had it as not in a sphere, and you just had incident light in a detector, you have all this light coming out of the filter. You don't detect that scattered light. You're like, oh, it's absorbance, but it isn't. So that's one of the problems with doing the transmission mode and not the integrated sphere mode. Okay. All right. So then we have to compute absorption from that. And we've taken a volume of water. Oh, what's our equation for absorption? So the instrument's going to give you the optical density. So how do we calculate absorption from optical density? We have to know the path length.
2.33
Ellen, right? 2.303. Optical density over the path length. What's the path length on the filter? Right, okay, so we've got a filter, and we're going to use the ones that are like 2.5 in diameter, 2.5 centimeters. And we turn it on its side, and we have a layer of particles that we filtered on there. And so that geometric distance is tiny, right? And it's also sort of embedded in the filters. Is that the path length of the ocean? Say it's a millimeter. Is that the path length of the absorption in the ocean? I mean, we took an ocean water sample.
Depends on how much you filter.
Depends on how much you filter. So you take your filter, it's a circle, an area, and then you take your volume of water, and essentially what you did is you took a column of water, the diameter of your filter, and that's your path length, the height of that column of water. So if you had a liter of water, which is in a bottle, take that same volume and squish it down to 2 centimeters, because that's the area, or the diameter, I'm sorry. And so that makes your volume go way up. So you can figure out, is it a meter path length? Is it a 2 meter path length? Depends on how much you filter, right? So as long as you know some geometry, what the volume is of a cylinder, you can do it. So 2.3 times the absorbance over the path length. The path length, we have to convert the volume filtered into a cylinder of water of area equal to the area of your filter, like where the stuff is on your filter, not the whole filter, but the effective area, times the height. And so the volume filtered over pi r squared, because it's a circle, volume over area is height, and that's your path length. So just make sure you have your units though, right? So your volume, if your volume is in mils and your area is in centimeters squared, it's centimeters cubed over centimeters squared, because a mil is a centimeter cubed. So make your volume in mils your area in centimeters squared. And then your units cancel to centimeters. Cool, but absorption is per meter. But you can convert because it's 100.
For effective area, that's the distance or radius that you actually agree on, right?
Yes, so you have to measure that diameter. And that's determined by your filter cup. It's okay, my technician did it 1,000 times on all of our filter rigs, on all of our cups. She did it with calipers, she came up with an uncertainty. So I will give you that. You don't have to do it, but you should do it for your own, just to make sure that your filter cups are the same as my filter cups. It's about, the radius is about 1.1 centimeter, about, if there's some uncertainty. Okay, so there you go. 2.303 times absorbance right out of the instrument, divided by your volume filtered in mils, your effective area, pi r squared in centimeters squared. That gives you absorbance per centimeter times 100 centimeters per meter times the conversion. I'm sorry it's tedious, but it's easy for me to tell all of you to do this in a group than have to tell each one of you at my spectrophotometer. And this way you know where all the numbers come from. It makes sense. Cool. Okay. Oh, do I want to do this? Yes, I guess I want to do this. Do I want to do this? I don't know. Yeah, we have to do this. So, one of the problems of putting particles on the filter pad, in addition to the things that we've already dealt with them, is that the filter pad itself is highly scattering. And so it actually does send a little bit of light backwards to get reabsorbed. And that is, we've already calculated the geometric path length from our volume, right? But if you have a little bit more absorption going on, you've effectively changed the path length because we have to go through it again, right? We have to go through that whole path length again if I'm backscattering from my filter through my sample again. And so that's just because we filtered it. If we had had it in suspension, we wouldn't see that. So we have to correct for that, and that is actually amplifying the geometric path length. And if some of you have worked with filter pad absorption before, you've heard of beta correction. Yeah. Beta for, I don't know. They probably had already used alpha, and they were on beta. So the way that we figure out what that is we take a sample that we could measure in suspension in a cuvette, and we put it in the integrating sphere, and you don't spill it on your PMT. And if there's any scattering in the suspension, it's okay, because it just is part of the whole scattering thing, and we just can account for that. And so you can measure the absorption by the particular material without scattering. And then we can take that same material and put it on the filter pad and measure it. And the difference is going to be that amount that got back because of the filter, that changed the number, that geometric path length by scattering back through my sample without entering the sphere. And so Gary Stransky did some really, really beautiful work in 2015 where you know him, everything is painstaking, right? Everything he does is like perfect. So he did this a bunch of times with a bunch of different kinds of samples, and he came up with a correction factor. The factor that is just the fact that you have things on a scattering filter. And so it's a very small correction. If you're interested, I actually derived the theoretical correction factor. It's about a factor of 2. And there's a reason for that, which we can talk about after we talk about radiometry. So he did it empirically, I did it theoretically, we got the same answer. We were so psyched after the fact, because we published differently, different papers, and found that out. So that's very cool. So To compute absorption, we're going to measure the baseline, subtract it from our sample. So there's our sample on the pad. There's our absorbance on the blank. And then we're going to apply the amplification factor of Darius and colleagues, which is a multiplier and a power. And then we're going to compute the absorption coefficient. So this is then corrected here. That's the number that goes in here. Volume over area, 100 to convert, and 2.303. And that's your quotient. It's written down. You can write it down. That's it. Okay. I may save in certain calculations. What time is it?
Roughly 40.
Yeah, we're gonna do certainty later. Da-da-da-da. There's uncertainty. We're gonna have error bars. It depends on how much you filter. We'll get there. I'm not gonna do it now. Okay. Oh, we don't have very many error bars. This is great. This is how you want to do it. See me later for details. Okay. We're gonna do the same thing, but we're gonna take our first scan on the particles, and then we're gonna check it with methanol and scan it again, like I told you, and we'll calculate the phytoplankton absorption. So we will do that. We've already talked about what does detrital mean, what do inorganics do. There's other things on those particles. We've talked about that. Okay. Summary. It's in your lab. Okay. AC. We don't talk about AC9s anymore because they don't make them anymore. However, if you have one, don't get rid of it. They are the best instruments. I've had them for years. They don't die. They're fabulous. Work them to the ground like a good old car. So they quantitatively measure absorption and attenuation. We have two paths, one to measure absorption, one to measure attenuation. We calibrate them with pure water. So that's the pure water will be a reference. We're gonna have to make measurements of the temperature of the water, remember, because we're gonna have to correct that. We also need to measure the salinity. Because we're calibrating with pure water at a certain temperature, our ocean sample will have a different temperature and a different salinity. They're not perfect configurations for absorption and attenuation, but they are pretty darn good. So, but there's some strategies that we're going to use. Okay, well that's good. Okay, so the reality is that we have a light going through a quartz cuvette going to a detector for absorption. And so that light comes in, maybe gets absorbed, maybe gets scattered, because there's particles. And sometimes it can be scattered backwards, it can be scattered forwards, it can reflect off of that quartz wall. And most of it, well, a lot of it makes it to the end to a detector where we have a big diffuser to collect anything that goes through that end we collect. So if it's forward scattered light, that's okay. We collect it, so it doesn't get included in the absorption. The other side has a detector that is very narrow angle detector. So it doesn't collect the forward scattered light, in theory, depending how big the detector is, pretty close. And so this part of the sensor, if it's only measuring transmitted light, it's not measuring, it's not collecting absorbed or scattered. It's measuring the attenuation, which is the sum of absorption and scattering. This tube is measuring absorption, and so by difference you can derive scattering, which is very helpful, all on a single instrument, and it's doing it out all the wavelengths. Okay. So it turns out that some of the scattered light isn't collected. Like anything that gets scattered out is not collected. And so we have to correct. There's going to be some scattering correction that you have to make for absorption. And it turns out that some of the scattered light is collected on this side because you can't have an infinitesimally small detector. And it makes a difference if your detector is this big or this big or this big. So when you do that, you just need to report your detection angle because it will make a difference. And you're going to do that later this week. and I think I say this later, I just completely blanked on my next slide, but the cool thing about these tubes is that most of the light just gets internally reflected because of the quartz to air transition. And so in fact, they're really highly reflective, and most of the light makes it to the end, which is great. It means it's a good absorption meter. Okay. So here's what we do. We get our instrument, we get it back from the factory in theory. We calibrate it in the lab immediately because it's been shipped. And because their calibration sometimes isn't as good as yours. So you calibrate it in the lab, and you're going to do that today. And if you're going to take it out in the field, like on our cruise, you might put it in a frame and you're going to strap it down, which can change it. Or maybe you have to lay it flat for some reason. You have to run it that way. So you should calibrate it again once you have it like in its deployment. And if it's super different, maybe you tweak it. So I always let it sit on something and I strap one side. I don't strap both sides because strapping both sides can tweak that perfect alignment that you've set up. Only strap one side. Yeah. And then depending upon where you are, you want to put black tubing because you don't want light traveling down this tube like a fiber optic and contaminating your signal. So always tape this. If you're deploying it, you might put copper tubing so it won't grow stuff. Having an air valve is nice. It keeps the bubbles out. I put the bottom in like a little seat and I bracket the top. Calibrate on the frame and then deploy. So when we do it on the boat, you're going to take it out, you're going to perch it, you're going to get all of the air out and then bring it back just beneath the surface so it doesn't suck any new air in, and then you can do your deployment. In the lab, we're just going to be getting the air out by squeezing the tubing.
Sorry, what does purge mean?
Purge means to get rid of.
The air.
Oh, purge the air. Yeah. I'll put air on there. Purge the air. Yeah.
So for purging, there's this special little thing that costs 50 cents at the top there. It's called a deacid one. Many people don't think about it. They don't put stairs and you don't have it.
And all the bubbles just like continue to like cycle around. And it just has a little tiny hole in it. And air wants to go up.
Data in real time, you don't even have it. You go a whole cruise, just come to data, come back home, start looking at the data. It's no problem. And it happens.
Yeah, we'll show you what it is. You can almost make one from just a Wi-Fi. Yeah. Yeah, don't skimp on the 40-cent thing when you're in a $40 million field program. Ever. And then a good idea is to calibrate when you get back. Yeah.
And the business layer, so there are pivots. Yeah.
Yeah.
So these two pivots are together in the.
They are right here, yeah. So that's one tube right there, and that's the other tube. So water gets sucked in, flows through both tubes, gets pulled. This is a pump, so it's pulling the water through. So you're measuring the water before it's gone through a pump. It's just being drawn through both of them.
Another lesson is you want to look at data in real time.
Yes.
Anything you can do to look at data in real time will help you know whether you collected or not. The going instruments over the side without being able to look at the data is at your own risk. It's really easy to correct on it.
So here's a profile that I can't even remember where we collected these data. I mean, it was a long time ago, but I don't know. This is just selected wavelengths of absorption, and it would look uniform, and then it went down. That was probably the picnic line, and then this is the deeper water. There was some messiness up here, but we measured. Oh, this was like near Friday Harbor in Orcas. Okay. And so we're like, oh my God, it's beautiful. We've got like really nice resolution. This is great. And then we looked at the data. And this is actually with an AC9, so it only had 9 wavelengths. And we're like, ooh, what's this? And why is this negative? And it was in both the mixed layer and the deep layer. So people publish this a lot. If they don't publish this with this, don't believe this until you see this. Because this spectrum is garbage. Just immediately, I can see it's garbage. There's something happening at 5:10. Okay, so luckily, we had a water calibration. It turns out it was just that sensor, either the filter or the detector, just needed to be recalibrated. And once you ran pure water through it, you could apply that calibration. And now we have a beautiful spectrum for the mixed layer and a beautiful spectrum for the deep layer. It's only 9 wavelengths, but here you can see the red absorption. So you always have to do a water calibration to save you from that.
Just like you do for your spectroscopy in your lab. Don't use the art books that use factory calibration. That means it's not.
Right. So here's a pure water scan that I think from maybe the last class for absorption and attenuation. And you can see that it's really different than what the factory would have done, because if it was the same as the factories, it would be 0, right? Pure water on both sides. They did pure water, we did pure water. I would say our water is cleaner because it's negative, right? So, so always doing these scans. So this is some work for Mike, looking at the Mike Twidarski at 412 as a function of days since calibration. And for his particular instrument, you can see that there's just a huge drift in instruments. And so if you don't do the calibration, you can be off that a lot. So just calibrate. That's the sensor uncertainty. Okay. Here's the temperature effect. Remember we talked about this? Well, here's the way you can calculate the correction for different temperatures and different salinities between water here, water there, and your calibration water. So you have to apply that correction. If you calibrate at 25 degrees with fresh water, but you measure a 10-degree ocean that's salty, you have not used the proper calibration standards, so you just need to correct for that. So Emmanuel is going to give you code to do that. But that's uncertainty due to natural variability. So the fact that your ocean is colder means that the absorption is less. The actual absorption is less because the water is colder. And you have to account for that. It makes a difference. Okay. So once you've corrected for temperature and salinity, suddenly you have these beautiful curves. These are actually multiple curves of one sample of attenuation and absorption. So corrected for pure water, it's even better. So we've done a pure water correction and we've done a temperature correction. And now what we notice is that our absorption has this big offset here. What absorbs out of the infrared besides water? Infrared subtracted water. It's got to be something. Or it could be scattering. So, for example, if you measured absorption of just phytoplankton, they don't have any absorption at 750, 0. Non-algal particles has a little bit, but not this much. So part of this is because of scattering. Remember, it's scattered out of the detector. So we have to do a scattering correction. That is a problem with the sensor, a sensor uncertainty problem. So you can either just subtract that value from the whole spectrum. And if you do that, what you're saying is that the scattering is equal across wavelength. That may or may not be true. We'll find that out this week. Does scattering have a spectrum? So this is the first approach. The other approach is to say, well, if I do a quick and dirty beam attenuation minus absorption, I can estimate a sort of scattering spectrum. And it looks like it's actually not very flat. So I can apply that shape and correct my absorption for the fact that maybe it's scattered a little more in the blue and a little more in the red. Okay, that's another correction scheme. We're gonna go through all of these tomorrow. So it's some fraction of that scattering. Okay. So that's, okay. So there are a couple of other schemes, and one thing that I will tell you is that in the integrating sphere, you don't measure scattering. So you can look at your absorption in the integrating sphere, this is what I do, and then I can apply that to my AC meters. So there's a bunch of different strategies that people use to correct for scattering, and you guys will get to do all of them. And Emmanuel will go through the data processing for the ACS, and you will get perfect, beautiful data of the attenuation, absorption, and scattering. And that's what you're ready to do. So I think, oh, we're going to talk about this in lab. Okay. We are done. I will post this so you can see the rest of it.
Oh, no.
Oh, I'm ready. I'm ready to go. I'm just thinking it's lunchtime.